Previously, we've talked about the literal Neville's method, in which we use our R formula recursion in order to actually build the literal polynomials that interpolate at x0, then x0 and x1, x0, x1, x2, and so on, until we achieve the polynomial that interpolates at all of our x values. Today, we're going to talk about something different. Instead of building the polynomials literally, I'm going to use that same R recursion to take a specified x value, feed it through the entire process, and what we will get at the end will be the value of the interpolating polynomial at that particular x value. All quantities that figure directly into the coefficients in the interpolating polynomial will be stored in a two-dimensional array with column and row indexes going from 0 to n. The pattern that we're going to have will be the same pattern as in the literal Neville's method, except we'll be executing the calculation with actual numbers for the x instead. Initially, we know only the x values from the data set and the function values that go with them. The function value that goes with a given data value, though, is the polynomial of degree 0, which interpolates at that single x value. So we're going to think of the f's as being part of the coefficients of our polynomial, and we're going to build a table that tells us the rest of them. Our indexes in the table are going to go from 0 to n. So in this specific example, I'll go from 0 up to 3. I is going to indicate to us which row we're in. K is going to indicate which column we're in. And based on our work so far, to find the coefficient that goes with x0 and x1, I'll need the coefficient that goes with x1 and the coefficient that goes with x0 only. Then I'll combine information from f of x2 and f of x1 to get the coefficient of the polynomial that interpolates at x1 and x2, likewise x2 and x3. Once I've done that, life becomes somewhat more complicated. I'm going to take information that interpolates at x1 and x2 and at x0 and x1, combine them. The smallest index is 0 and the biggest index is 2. By using my R formula, I'll be able to get the coefficient that goes with the polynomial that interpolates at x0, x1, and x2. And likewise, by combining information about the polynomial at x2 and x3 with the polynomial at x1 and x2, we'll be able to get the coefficient of the lead term from the polynomial that involves x1, x2, and x3. And then lastly, we'll combine these two pieces of information to obtain the value of the polynomial that interpolates at x0, x1, x2, and x3. This is just one way of many that you could organize these calculations. Following the work that we've done previously, I can already begin to work towards my code. I'm going to have my table, capital T, indexes 0 to n, 2 of those indexes. I'm going to put the function values from my data set into column number 0. Then I will generate columns 1 through n in the way we've previously described. I'll have, for each I going from k to n, so I is the bigger one, the number in row I, column k is going to be the number in row I, column k minus 1, minus the number that's in row I minus 1, column k minus 1, divided by the difference of two of the x values. I have to be careful to index those x values correctly. I've written in not the actual calculations, but the indexes of the x that's going to go with those calculations. Here in the I equal 1 row, k equal 1 column, I'll have 0 and 1, followed by 1 and 2, 2 and 3, and so on if I had more rows. The difference between the two indexes is a constant value. At the beginning, the larger index is I, and the smallest index is 0. Let's see if that holds up. Based on our recursion before, I'll have 0, 1, and 2, 1, 2, and 3. At the top, the smallest index is 0, and the biggest index, 2, is equal to the I that I'm sitting at. Then I increase by 1 to get these. In the k equal 3 row, the biggest index is 3, the smallest index is 0, so the smallest index is always going to be 0, and at the top of the column, the top that we're actually going to calculate, the I and the k are the same value. As you proceed down a column, both indexes increase in lockstep with each other to keep the difference between the indexes constant. So if I literally want to carry out Neville's method, but not form the literal polynomials, initially, I'll put the function values into column 0 of my table, then do k equal 1 to n, do I equal k to n, tik. This is the entry that's going to be in row I, column k, and I'm forming this as a lower triangular structure, taking into account all the indexing that we've done. We're going to calculate x minus the smaller x indexed value times the number that's immediately to the left of the thing I'm calculating, minus x minus xi times the number that's immediately to the left and 1 unit up in the table, divided by xi minus k. If you run this algorithm, the number that's left sitting in row n, column n, is going to be the value of the interpolating polynomial at x. Of course, this is a little awkward because if you think about having a table that has n rows and n columns in it, there are n squared numbers in that table. If you remove the diagonal, there'll be n squared minus n, which has to be an even number. The number of quantities in the lower triangle will be n squared minus n divided by 2. And if you include the diagonal, which we have to, you get half of n squared minus n with n added to that. Now, each one of these numbers is going to require 2 subtractions, 2 multiplications, and a division. So the total amount of work is about 5/2 n squared plus n floating point operations. This is just to do one evaluation of the interpolating polynomial. This seems a little bit excessive, and as we'll see, there'll be a way around this. So let's look at not actually doing that. If you remember, we convinced ourselves that you can write the interpolating polynomial in this format. The A0, A1 through AN are constants determined by the data values. Also, we had a fancy name at one point. A0 is actually going to be the polynomial of degree 0 that interpolates at x0 only. A1 is going to be the coefficient of the linear part of the polynomial that interpolates at x0 and at x1. A2 will be the coefficient of the polynomial that interpolates at x0, x1, and x2, and so on and so forth. When a person talks about the lead coefficient of a polynomial, they're talking about the coefficient, which isn't 0, that goes with the highest power in the polynomial. I'm going to momentarily introduce another notion, though. I'm going to think of the front coefficient. And what I mean by that, for example, is I could have a quadratic and I could have another quadratic. If I made some number times the first one plus number times the second one, generally speaking, that's going to be a quadratic. But if you pick the numbers just right, some of the terms can cancel out. If I look at 3 times this polynomial plus 2 times that polynomial, the x squared piece cancels out. Strictly speaking, the lead coefficient of this polynomial is the 11. However, if you look at the coefficient that goes with the highest power of x that could show up in the polynomial, that would be the 0. It canceled out in this case, but usually doesn't. I'm going to call this coefficient the front coefficient. Usually it's the same as the lead coefficient, but this one can be 0. I've got 2 observations to make, and then we'll be able to get the Newton divided difference form. Number 1, if P is a polynomial and C is a constant not equal to 0, then the front coefficient of P of x divided by C is what you get when you take the front coefficient of the polynomial and divide it by C. That looks very mysterious, but there is less there than meets the eye. For example, suppose that your P polynomial was 3x squared plus 5x plus 6, and the C was 7. Then if you take the polynomial and divide it by 7, if you look at what you get for a front coefficient, you get 3/7, which is the front coefficient of the original polynomial on top divided by 7. That's all I mean by that. On the other hand, if you look at a polynomial P of x, it has some front polynomial. If you multiply that by a polynomial of type x minus a constant, then the front coefficient of the result is the same as the front coefficient of P. The reason for that's very clear. If you look at x minus 5 times 6x squared plus 5x plus 1, for instance, if you were to actually multiply that out, the highest power would be an x cubed, and because this is 1 times x minus 5, what you'll actually have is 6 times x cubed. So once again, there's nothing very deep going on here. I'm going to think of the polynomial that interpolates at xi through xk plus 1. We determined that that's x minus xi times the polynomial that interpolates at I plus 1 through xk plus 1 minus x number k plus 1 times the polynomial that interpolates at xi through xk. Now, we made up a fancy symbol a long time ago for the front coefficient of the polynomial that interpolates at xi through xk plus 1, and it was this symbol. That must equal the front coefficient of this quantity, because this quantity is r of x, but this is a polynomial divided by a constant. So I can take this 1 over xk plus 1 minus xi out front. This quantity is 1 over xk minus xi times the front coefficient of this polynomial minus this polynomial. This is where I had to make the distinction between the lead coefficient and the front coefficient. This is 1 over xk plus 1 minus xi times the front coefficient of just this part minus the front coefficient of just this part. On the other hand, we just said a minute ago that if you have x minus a constant times some polynomial, the front coefficient of the result is the same as the front coefficient of, in this case, the q polynomial, and in this case, the p polynomial. So this must be true. Putting the pieces together, the front coefficient that interpolates at xi through xk plus 1 is the front coefficient that interpolates at I plus 1 through k plus 1 minus the front coefficient of the polynomial that interpolates at xi through xk divided by xk plus 1 minus xi. We are going to be able to take two polynomials of degree 0, two function values, and combine them using this formula to get the front coefficient of a polynomial that interpolates at 2 points. We'll do that for several points. We will combine polynomials that interpolate at 2 points. We will get the coefficients of the polynomials that interpolate at 3 points, and we'll continue this until we've gotten all of them. One thing to mention is, though, I do need to be careful about the indexing because I've arranged my calculation so that my numbers appear in sort of a lower triangular pattern. If I had decided to use an upper triangular pattern, the formulas would look different. We need an example. So I'm going to let n equal 2, meaning since I have n plus 1 data points, I'll have 3 data points. I have x values, x0, x1, and x2. These coefficients that are based on interpolating at a single point are just function values. So f at x0 is 10, f at x1 is 4, and f at x2 will be 7. I need to calculate 3 things. I need to calculate f bracket x0, x1, the front coefficient of the polynomial that interpolates at x0 and x1. I need to know f bracket x1, x2. That's the front coefficient of the polynomial that interpolates at x1 and x2. And once I have these 2 things, I will combine them and get the front coefficient of the polynomial that interpolates at x0, x1, and x2. And the reason that we want to do that is, in terms of our earlier language, that's a 0, that's a 1, and that's a 2. We will know the coefficients of the polynomial written in the form that we've been talking about. But thanks to that recursion relation that we've figured out, f bracket x0, x1 is f bracket x1, just the function value at x1, minus f bracket x2 divided by x1 minus x2. That's perfectly straightforward to calculate. You get -3/2 for an answer. F bracket x1, x2, bigger indexed f bracket number minus smaller indexed one divided by x number, biggest index out of the bunch is 2, smallest index is 1. Do the arithmetic, 3/5. So we know this number, we already knew these numbers, we calculated these. All we have to do is calculate f bracket x0, x1, x2, and we'll be done. Remember how this goes? I'm going to look at one of these quantities, which I might as well go on and start calling divided differences because that's their name. My indexes are 0, 1, and 2. I want to look at the divided difference based on one less data point, but I want the one with the bigger indexes. That would be x1 and x2 minus f bracket. I want to have two quantities inside the brackets, and I want them to go with the smaller indexes. That would be x0 and x1 divided by x number, biggest index in the set, which is 2, minus x number, smallest index in the set, which would be x0. And after doing the arithmetic, it turns out that that last quantity, this one, is 7 divided by 30. Now, what we said earlier was this is going to be the constant coefficient in my interpolating polynomial. This is going to be the coefficient of x minus x0, and that's going to be the coefficient of x minus x0 times x minus x1. x0 is 1, x1 is 5. If I believe what I just said, then this has to be the interpolating polynomial. As a sanity check, I'm going to use my calculator to calculate the values of that polynomial at x equal 1, x equal 5, and x equal 10, and I better get 10, 4, and 7 back for an answer, or there's something wrong with my reasoning. So I'm going to take 1 and store it into my x variable. I've already checked this to make sure that there was no flub here. So I'm going to say second enter. We're going to calculate 10 minus 3/2 times x minus 1 plus 7 over 30 times x minus 1 times x minus 5. The result ends up being 10, like it's supposed to be. I'm going to store 5 into the x variable and then calculate the value of the polynomial again, which turns out to be 4, just as it's supposed to be. Then I'm going to take x2, which is 10, store it into the x variable, calculate the polynomial, and get 7. This is a polynomial of degree 2 or less that produces the correct function values. We know there is one and only one of those. This shows that the calculation is correct. The only remaining issue is once we've calculated this, I'll go on and call it what we'll call it, the Newton form, the Newton divided difference form for the interpolating polynomial. How can we evaluate it in some efficient manner? Next time, we will talk about nested multiplication and start thinking about coding procedures. If you haven't looked at the video on files, be sure to do that because we're going to be doing some file stuff pretty soon. I hope everyone's having a good day. I'll talk to you again soon.